Hey everyone, welcome to the channel and here we explore all the things related to computer science operating systems. Whether you are a student, a professional or just someone curious about how technology works, you are coming to the right place. In today's video, we are diving deep into the crucial concept in operating system, multiple processor scheduling. As the name suggests, this is all about how operating system manage and distribute tasks across multiple processor or cores within a system, with multi-core processors becoming the norm in everything from our phones to powerful servers. Understanding how these systems efficiently allocate resources is more important than ever. Next, introduction. Multiple processor scheduling describes the tasks are distributed across multiple CPUs to boost performance. It involves deciding which task runs on which CPU, aiming for higher throughput by processing tasks concurrently. A key challenge is load balancing, ensuring work is evenly distributed to prevent bottlenecks and maximize CPU utilizations. Essentially, it's about making the most of having multiple processors working together. Multiple CPU enable load sharing, distributing work for better performance. However, this makes scheduling more complex than with a single CPU, as the scheduler must decide which CPU runs which task. Even with identical CPUs, the scheduler still needs to balance the load and assign the task efficiently. In next, approaches to multiple processor scheduling. Let's talk about two ways to manage multiple processor. One is asymmetric and another one is symmetric. First we see asymmetric multiprocessing. Imagine a one master processor calling all the shots. It handles all the scheduling decisions, deciding which task run where, and all input output operations. The other processor are just workers executing the actual program. This is simple to implement and reduce the need for processor to share data directly. But the master processor can become a bottleneck. And next one is symmetric multiprocessing. Now imagine each processor being independent and capable of scheduling its own work. There's no single master. Each processor can also handle I/O. This is more complex to set up, but it distributes the workload more evenly and is generally more efficient. For an example, having multiple independent chefs in your kitchen, each deciding what to cook and handling their own ingredients rather than one chef handle everyone around. And next is processor affinity. Processor affinity means a process prefers to run on the same CPU it's currently on. Why? Because when a process runs, its data gets stored in the CPU cache. If the process keep running on the CPU, it can quickly access that cached data, making it much faster. Switching CPUs means the process loses this cached data, leading to slower performance. So, stitching with the same CPU is often more efficient. And when a process moves from one CPU to another, it creates a problem with the CPU caches. Each CPU has its own cache, a small, fast memory that stores frequently used data. When a process runs on CPU, it loads data into the CPU cache. If the process moves to the different CPU, one is cache invalidation. The first CPU's cache now has data. The process data that's no longer running there. This data needs to be removed or invalidated to make space for new data. Next is cache repopulation. The second CPU's cache is empty or doesn't have the process data. The process needs to load its data into new cache, which takes time. Both cache invalidation and repopulation are costly operations. They slow down the system. Therefore, to avoid these costs, Most SMP systems try to keep process running on the same CPU. This is processor affinity. It's like having a dedicated desk in your office. It's much more efficient to stay at your desk. The processor affinity comes in two flavors. One is soft affinity and another is hard affinity. Soft affinity. The OS tries to keep a process on the same CPU for performance reasons, but it's not a strict rule. The process might move to the another CPUs if needed. Next one is hard affinity. The process is guaranteed to run only one specific set of CPUs. This process itself can specify which CPU it's allowed to run on. This offers more control but can also limit scheduling flexibility. And the next, load balancing. Load balancing distributes workload evenly across CPUs in systems where each CPU has its own task queue. This prevents some CPUs from being overloaded while others sit idle, maximizing performance. And next slide. Um, Load balancing uses two main methods. One is push migration and another one is pull migration. Push migration. A process regularly checks CPU loads and pushes tasks from overload CPUs to idle or less busy ones. Pull migration. An idle CPU actively pulls tasks from a busy CPU to execute.
And the next is multi-core processor. Multi-core processor pack multiple CPU cores onto a single chip, each core acting like a separate processor. This is faster and more power efficient than having separate chips. However, multi-core system can make scheduling more complex as the scheduler now manages tasks across cores on the same chip, potentially introducing new challenges related to resource sharing and inter-core communication. Memory stall happens when a CPU has to wait for data from memory. This often occurs due to a cache miss, data not being in the fast cache memory. During a memory stall, the CPU can waste a lot of time, sometimes up to half its time just waiting. Next, to combat memory stall, CPU waiting for data, modern CPUs use multi-threading. A core runs multiple hardware threads. So if one thread stalls waiting for memory, the core can switch to another thread. There are two types: coarse grained and fine grained. Threads switch only after significant events like a long memory stall in coarse grained, and the fine grained threads switch at much finer level, often after each instruction, maximizing CPU's utilization. Coarse grained multithreading. Coarse grained multithreading switches threads only after long delays, like a memory stall. Um, while this hides some latency, the thread switch itself is expensive because the CPU's instruction pipeline must be emptied and refilled, causing performance hit. Next is fine-grained multithreading. Fine-grained multithreading switches threads at a very frequent instruction by instruction level. Because the hardware is designed for this, the switching overhead is minimal, leading to better CPU utilization. Next, with virtualization, a single physical CPU can appear as multiple virtual CPUs to different virtual machines. The hypervisor schedules these VMs onto the physical CPU, making even a single core system behave like a multiprocessor system. Each VM has its own guest OS, and the hypervisor manage how these guest OS share the underlying hardware. In virtualization, a host OS creates and manages virtual machines. Each VM runs its own guest OS, where application reside. Different VMs can be assigned to different tasks. Users or even run different types of operating systems like real-time or time sharing on the same physical hardware. Next, visualization can mesh with the guest OS timing. A guest OS might think it's getting as 100 ms time slice, but due to the hypervisor scheduling of the physical CPU, that 100 ms slice could actually take much longer in real time. This can negatively impact time sensitive operation within the guest OS. And next, because the hypervisor schedules the physical CPU, a guest OS time slice can get structured out. For the guest OS thing, it is 100 ms slice might actually take a second or more in real time if the system is busy. This leads to poor performance and slow response times for user inside the virtual machine. Even though the guest OS think it has full control of the CPU, it's like the guest OS is running on the CPU that's sometimes unavailable due to the hypervisor's management of the actual hardware. And next, virtualization can measure timekeeping within VMS. Timers in VMS might trigger late because they based on the VMS perceived time, not the actual time on the physical CPU. This can throw off the guest OS scheduling, undoing its attempts to manage process efficiently. And in conclusion, CPU scheduling is essential for keeping the CPU busy and running tasks efficiently. Multiprocessor system make scheduling much more complex, requiring careful strategies to balance the workload across processors and optimize performance. Thank you, guys.